Good afternoon, everyone, and welcome to today's USACM Student Chapter Seminar. Today, we are delighted to have Graham Pash from University of Texas, Austin, who will be speaking about scalable Bayesian inference to enable personalized clinical decision-making in oncology. Graham Pash is a final year PhD candidate in the Computational Science, Engineering, and Mathematics program in the Odin Institute at the University of Texas at Austin, where he is advised by Professor Karen Wilcox. He received his MS from the same program in 2022 and earned a BS in both applied mathematics and mechanical engineering from North Carolina State University in 2019. His PhD work has been supported in part by the Department of Energy's Computational Science Graduate Fellowship, through which he completed 2 practicums at the National Renewable Energy Laboratory. His current research interests are in the intersection of computational science, inverse problems, and optimization as enablers for digital twins. His thesis research focuses on the development of methodologies to support precision oncology in active collaboration with the Center for Computational Oncology at the UT Austin. Please join me in welcoming Graham Pash. Now, Graham, the floor is yours.
So thank you very much for the very nice introduction. And thank you very much for the invitation to come give a talk. This is a really nice venue, and it's been awesome to go back and sort of look at some of the older videos and see the other talks. So I'm really excited. So like you were all told, I'm going to be talking about scalable Bayesian inference to enable personalized clinical decision making in oncology. So it's kind of a mouthful. So I'll sort of start by unpacking what I mean by that. I'll talk about what I'm then going to do, how the specific problem that I'm working on solving. I'll give a case study, and then I'll sort of follow up with some future directions that I see. And I want to note that this is joint work with some great collaborators for the Center for Computational Oncology. So Umberto Villa, David Hormuth, and Tan Yankelov, as well as my advisors, Karen Wilcox. So a lot of the motivation for this problem sort of comes from the idea that we want to build a digital twin of sort of a patient. And this is, I think, one of these concepts that if you ask 10 people for a definition, you'll probably get 11 different definitions back. And so I like this one, particularly from the National Academies, just to sort of put us all on the same footing. And so it says a digital twin is a set of virtual information constructs that mimics the structure, context, and behavior of a natural, engineered, or social system or system of systems. It's dynamically updated with data from its physical twin. It has a predictive capability, and it informs decisions that realize value. And what's key is that this bidirectional interaction between the virtual and the physical is central to the digital twin. And so when I hear these sort of, parts of the definition, dynamically updated with data, to me, that sounds like some kind of data assimilation or inverse problem. Predictive capability, this is sort of the more classical forward modeling. So what are the specific governing equations that are driving the system? And then informs decisions that realize value. To me, this sounds like some kind of optimal control or optimal decision-making problem. And so what it might look like in this specific setting, we'll be focusing today on glioblastomas, so aggressive brain cancers. So there's a real patient out there in the world with this disease, and we hope that we have some kind of computational model that will sort of tell us something about the nature of this disease. And now, of course, we don't get perfect information about the state of the patient's health. And so we get these sort of like sparse, noisy observations that are sort of indirect and tell us something about the disease itself. And so in this setting, it's going to be these multimodal MRI that are acquired during the routine patient visits when they come in for checkups. And then we hope to integrate this medical data with some kind of governing equation or a computational model so that we can calibrate model parameters in a patient-specific manner. And we want to do this with uncertainty because we want to be able to make probabilistic forecasts of the tumor progression. And the idea is that if we can predict this spatiotemporal evolution of the tumor growth and critically how a patient will respond to treatment, then we have some hope of actually controlling the therapeutic intervention, stepping in and optimizing the care that an individual receives away from sort of the one-size-fits-all standard of care that they otherwise would. And so to me, digital twins are really about exposing these rich interactions in the outer loop things like data assimilation, uncertainty quantification, optimal control, optimal experimental design. These are things that people have been working on very hard for many, many years, many, many decades. But digital twins are sort of how you bring together the data with the models, with the uncertainty quantification to enable feedback control and design of the system. And then I'd argue that there's a real need to personalize healthcare. The way that the clinical trial system is currently stood up, it's very rigorous, but what it delivers by virtue of grabbing a cohort of patients and testing one intervention is that it delivers an intervention that performs well across an average cohort, but not every individual is an average patient. Everyone is unique. And so we think that we can help improve decision making at the level of the individual with our computational models. And then that will drive improvement in outcomes at the population level as everyone receives a better therapy. And so sort of the outline of this talk is now I'm going to get into the inverse problem that I'm setting up and solving. So I'm focusing today more on sort of that top loop. So how do we assimilate this data? So I'll walk through the formulation, the mechanistic model that we're using to model this tumor growth, the clinical data that we have access to, as well as the implementation. Then I'll get into sort of a case study where all of these things come together. I'll give some concluding remarks. And if you're interested in following along, you can follow this QR code. So we have sort of a manuscript that describes a lot of these methods that's under review at JCP. I'm going to take a quick break to drink some water. Okay. So I'll start with what is an inverse problem. And to me, it's a very simple sort of one-liner statement. It's if you give me a model and you give me some data, can we infer those model parameters? So do we know how to parameterize the model? And so we have to mathematize this a little bit. And so we're using this additive Gaussian noise model. So we're making an assumption that our data D is going to come from some forward model F that has model parameters M. And then of course, we don't get perfect measurements. And so they'll be corrupted with some kind of Gaussian noise. So what makes this difficult in this setting is that we get noisy and infrequent data. So these MR sequences are not collected very frequently, and we don't get that many of them. And so while we might get a tremendous amount of information when we do get these sequences, we typically don't get very many of them throughout the course of treatment. The forward model that we're going to be considering today is going to be nonlinear, so it's going to make this inverse problem difficult. It'll be non-convex. It's going to be ill-posed in the sense of Hadamard, which means that there are multiple sets of parameters M that, given the noise level, could reconstruct the data the same way. And then it's going to be computationally expensive, right? To faithfully recreate the anatomy of a patient and to solve these dynamics is going to be a hard numerical problem. And so the models that we're going to be using are these partial differential equation models. And so we're going to define our forward model comes through some residual form of the PDE. So this is an abstract way to write your partial differential equation where we solve for the state U that is going to depend on the model parameters M. And then we have this observation operator here, B, which is going to take us from sort of, imagine that taking you from finite element solution to the data space that the data lies in. So that might be a voxel data space for the MR images. And then we're going to set up this nonlinear least squares formulation where we hope to minimize the model data misfit weighted by the noise that we think is in the data. And then we're going to have some kind of regularization. And so now we need to be able to balance these two terms. How much do we trust the data and how well do we fit the data versus how well do we inform some kind of structure in our reconstructed solution? And so I think one sort of really concrete example to latch onto is sort of this deblurring example where I want to add noise to this true image, and then I want to invert back for this original denoised image. And so my forward model here is just the identity. It's just the parameter is the forward model. And so you can see there's sort of this Goldilocks region between these inversion regimes. So in the case where my regularization dominates and I say I want some kind of smooth reconstruction for the surface, or for the image, I kind of blur out important features to me, like the horns of my longhorn here. And then on the other extreme, if I trust the data too much, then I'm reconstructing the image with the noise itself. So somewhere between the two, where I balance the structure that I encode into the problem and the data that I have, I can get some kind of nice reconstruction. And so one very natural way to do this with uncertainty is to reach for a Bayesian formulation. So it'll give us a mathematically rigorous way of inferring parameter distributions so that we can quantify uncertainty. And so this happens through the posterior distribution. which can be expressed as this Radon-Nikodym derivative between the posterior measure and the prior measure that's proportional to some likelihood. And for additive Gaussian noise, we can write down explicitly what that likelihood is going to be. And so it's going to be exactly sort of this data fidelity term that we had previously. And so now our solution is not one set of parameters that we think best matches the data, but it's rather a distribution of plausible parameters that match the data. And then on the other side of how do we encode structure, so the role of regularization is going to be handled by the prior distribution. And so we're going to be using a Gaussian prior. Again, we're working with partial differential equation models. And so we're going to be thinking about things first in infinite dimensions before you actually discretize to be able to solve the problem. And so we can, one nice thing about a Gaussian prior is that it's going to guarantee that we have a well-posed infinite dimensional posterior. And it's going to be of the form here where we can see that we have, again, this model data misfit term, this data fidelity term, and then another term coming from the prior itself that looks like a regularization term. And so we're using a very specific choice of covariance. And so it's basically through the inverse of this elliptic operator. But what I want you to think about is that we can sample this field by solving this partial differential equation here. And when we get samples, we get something coherent on the entire sort of unstructured geometry. So when I sample, for example, a diffusion coefficient in a brain, under the hood, I'm sampling this covariance structure, but I get realizations on the entire domain. And so there's some sort of natural connection here between the deterministic inverse problem and the Bayesian inverse problem. And it comes through sort of noting that the posterior can be expressed as this data fidelity term and this regularization term, where this role is played by the prior. And so if we search for the maximum a posteriori point, so sort of the mode of the posterior distribution, we get that by minimizing the log posterior. And when we write all this down, we find that we end up with exactly the same deterministic inverse problem again. So if we want to find the mode of the posterior distribution, it's equivalent to solving a deterministic inverse problem. And there's been a lot of work on how you solve these PDE-constrained optimization problems over the last 2 decades. And so this can be done very scalably with Newton-Krylov methods. And so now what we're going to do is sort of try to shortcut accessing the true posterior, which would only be available through something like Markov chain Monte Carlo for the case of a nonlinear forward model. But on the other hand, the prior might not actually be a very good reference measure. And so we're going to try and split the difference here. And so we're going to solve this deterministic inverse problem. It's going to give us a location that we then want to lay down a Gaussian sort of low rank posterior down upon. And then now we can either sample directly from that, or we can use that as a much better reference measure to actually access the true posterior with a sampling method. And so the Laplace approximation centers a Gaussian at that maximum a posteriori point. So we know how to compute this point now. And so the challenge is, how do we invert the Hessian, right? So once we discretize these random fields, they're going to be very high dimensional, right? So if you use first order Galerkin projection for finite elements, you're going to have as many degrees of freedom as you have vertices in the mesh. And so you might have, say, order 1,000,000. So being able to form that Hessian is going to be very, very challenging in the first place, let alone inverting it. And so we have to sort of bring some new ideas here for how we can do that. And so our idea is that we should decompose and we should solve for only the directions that are actually informed by the data. And so what we do mechanically is we take the Hessian and we break it into its 2 components, the component coming from the prior and the component coming from that data fidelity term. We solve this generalized eigenvalue problem for the eigenvalues and eigenvectors, and then we apply the Sherman-Morrison-Woodbury formula. And so when we now go to invert the Hessian at the map point, we break it into its 2 components, we apply our identity, and what happens is that we have our prior here, which we know how to discretize and access, and then now we have some low rank representation for the data update to the posterior. And so when we need to access the posterior covariance, we can do this very efficiently because this is small and compact, and then we can already assemble and use this. And so sort of that's all the machinery that we're going to use to solve this inverse problem. So the idea is that we're going to receive some data, we're going to solve for the map point, we're going to then invert the Hessian at that map point, and then we're going to sample from that to sort of do our posterior push forwards. But now I need to tell you something about the actual model that we're using, as well as the data itself. So I'll start with the model. Unfortunately, in the field of computational oncology or tumor modeling in general, um, we're not so lucky as, say, in fluid dynamics, where there's a Navier-Stokes equation that can be derived from first principles, right? And so instead, we rely largely on phenomenological modeling. And in particular, we focus on two hallmarks of tumors. And so that's the ability of the tumor to infiltrate healthy tissues, as well as the tumor to vascularize itself and sustain itself where it already is. And so we take these two assumptions. We model the infiltration with the diffusion process. We model the proliferation with a logistic growth process. And this yields this sort of semilinear parabolic PDE. It's a Fisher KPP type. And then the treatment terms we sort of take into the right-hand side, the forcing function. And typically for brain cancers, although there are emerging immunotherapy methods, I think by far the two most widely deployed methods would be radiotherapy and chemotherapy. And so we model radiotherapy by sort of collecting the times that you would come in and radiotherapy would be applied. And then we use this standard linear quadratic model to estimate the survival fraction. So we assume an instantaneous effect. The radiotherapy beam comes in, it hits the tumor. Some fraction of cells are killed, some fraction of cells survive, and we compute this with this linear quadratic model. And then chemotherapy, similarly, we have a collection of times where we actually take the chemotherapy agent, and then we have sort of a decaying exponential washout for how that concentration of chemotherapy agent leaves the bloodstream. And so combination chemo radiotherapy is going to be handled by combining these two source terms. So I need to tell you about the data that we use to inform these models. I'm not a radiologist, and I don't anticipate anybody in the audience is a radiologist either. But what I hope people can sort of get from these images are that these different MR sequences are providing us complementary information. So some of them are telling us something about the patient anatomy. So T1 and T2 tell us something about how the white and gray matter and the cerebral spinal fluid is ordered in a patient's anatomy. T1 with contrast enhancing agent tells us something about the necrotic tumor core, something about sort of the enhancing tumor regions. And then FLAIR can tell us something about edema or swelling around the tumor regions, sort of diffuse areas of tumor. And then we use this apparent diffusion coefficient to estimate the tumor cellularity. So ultimately, we're going to be evolving the tumor volume fraction, which is related to the cellularity divided by some kind of carrying capacity. And so what we do is we take these T1, T2 images, we perform this anatomic segmentation, we perform mesh generation, and now we have, at this point, a patient-specific computational domain that will evolve these equations on. So we're going to fix the domain here, sort of at the first set of images, and evolve the dynamics on this throughout time. Then we take these other images and either using sort of a machine learning algorithm to perform tumor segmentation, or if you're lucky enough to have collaborators to collaborate with radiologists, you can actually get tumor segmentations from them. We take those tumor segmentations, we combine them with the apparent diffusion coefficient to estimate the cellularity. We take all of these things together, and at this point, we have a snapshot in time of the patient's tumor state. And so if the patient comes into the clinic again and a new set of images is collected, of course, now we have to do some kind of registration between these two. They don't sit in the scanner the same way every time. But we can perform this operation, and then now we have another snapshot of the patient tumor state. And if they come in another time, we get another snapshot. And so in this way, we can sort of develop snapshots of this tumor volume fraction longitudinally, and now we can calibrate our model to that data. And so at this point, we can sort of put everything together and we can sort of generate a forward simulation of tumor progression. And so we're using Phoenix for the finite element assembly. We're using PETSI for the nonlinear and linear solvers. We're using this HippieLib package for the inverse problem modeling. And I want to point out that access to quality data is a challenge, right? So we're very lucky here at UT to be able to work with collaborators at MD Anderson and sort of get access to world-class data. But most patients are not seen at world-class research facilities. They're seen in sort of community clinics. And so the data that we use are the data that would be available in those settings. So we made a conscious choice to try and make the methods as general as possible. One last thing is that that's a very nice video, right? But if it takes us a month to generate that video, that's not particularly useful to a clinician when they have to make decisions about how to treat a patient. And so for us, we're leveraging high performance computing to really enable simulation, inversion, and decision making on a clinically relevant timeline. And so what I'm showing are two strong scaling studies done at Texas Advanced Computing Center and their Frontera supercomputer, where the top one is the strong scaling within a node. So we get very, very nice strong scaling in node. And then this is the strong scaling between nodes when we have multiple nodes. And we see that we have decent scaling here as well. But the takeaway is that we can do a 6-month forecast of tumor progression in about a minute. So we can actually bring down the computational cost low enough that we can perform the inversion in about a day. And then we can now draw from the posterior and generate the posterior predictives in a few hours. So we can actually give information to clinicians on a timeline that works for them. And so now I'll take a quick water break. If anyone has questions, now's probably a good time before I get into the case study.
Yes, good presentation. I have a quick question on slide 18. I joined very late, so I actually do not know the aim of the presentation. But then I wanted to know the kind of data you are considering over here. Is this data coming from a male patient, a female patient? Are you considering those kind of age difference using this data?
Yeah, so I'll sort of break the question into two. So the idea is that we want to be able to calibrate these diffusion and proliferation rate parameters in a patient-specific manner. And so we want to fit this PDE model to the data that we're seeing from an actual patient. In the cohorts that we looked at, we have both male and female. Typically, glioblastomas are something that occur later in life. So I haven't done sort of a statistical study on the data set, but my guess is that more of the patients are older in nature. But we're using sort of well-established neuroimaging software to sort of do the pre-processing of the geometries. So I don't think that there are, in this study, I don't think that there would necessarily be a reason to sort of separate male and female patients. Yeah, if that answers your question.
Yeah. And then are these data coming from MRI or TC scans?
These are MRI data, yeah. Okay. So now I'll get into sort of a case study, sort of demonstrating the idea and give some concluding remarks. So the setup for this case study is that we really want a controlled setting for verification of this method. So sort of, can we solve this inverse problem and to what fidelity can we solve this inverse problem? And then we want to look at assessing alternative imaging schedules. So like I said, imaging is not necessarily standardized, and how frequent the data is collected can have a big impact on the quality of the reconstruction and your ability to faithfully predict tumor dynamics. And so we want to assess, sort of how access to data changes the reconstruction and your ability to predict. And so what we're doing is taking a real geometry and initial condition from clinical data. We're generating data on a high fidelity mesh. We'll invert on a lower fidelity mesh. And we're assuming sort of heterogeneous diffusion in the gray and the white matter. And then we corrupt that synthetic data with 2% Gaussian noise. And so the disease progression looks something like this. So this is the patient initial condition. We allow for untreated growth for 2 weeks. And then we apply chemoradiation, sort of the STUP protocol, which is the standard of care for the next 6 weeks. Then we allow for untreated growth again for another month. And then after week 12, we calibrate, and with the hope of making predictions at week 16. And so what we see in the reconstructions, so these are different axial slices of a patient's brain. And these are sort of the tumor overlays here, and the reconstructed diffusion and proliferation fields, as well as the error. What we see is that you only are getting information about the tumor state where the tumor is, right? So the prior is sort of dominating here on the right hemisphere, where there actually is no data, where the tumor is not growing. And we have a hard time picking up sort of heterogeneous diffusion between the gray and the white matter. But for the proliferation rate, which is assumed to be homogeneous, we're actually doing a pretty decent job at reconstructing it. And so there are all kinds of questions about how much data noise can we handle, and are these parameters structurally identifiable? But to the level that we can avert using this methodology, I think that we're actually doing a pretty decent job reconstructing these parameters. And you'll see that sort of in the posterior predictives in 2 slides. But what's really interesting is not necessarily, sort of specific deterministic inversion of the map point, but really how can we quantify how valuable an image is? So for this sort of study, we can think back to this generalized eigenvalue problem that we were solving, and we can sort of have the notion that the eigenvalues here are telling us how well informed these modes are, these eigenvectors, right? And then the eigenvectors are going to show us where it's well informed. And so what we see is sort of, okay, this is a very nice result. So if we image daily versus weekly versus fortnightly, we can see that we're extracting more information from the data, and we're better informing the individual modes. And then if we look at sort of where is informed, this is the first mode. And so it's sort of centered around where the tumor is. And then as you go down and you look at higher and higher frequency modes, you pick up higher and higher frequency content. But it's important to note that sort of this mode for the daily case is about as well informed as this mode is for the weekly case, right? So we're actually inferring something useful. But what a clinician might care about is something like, what is, the impact on the quantity of interest, right? So we looked at 2 of these: tumor volume, so just how large is the tumor burden, as well as this concordance correlation coefficient, which is sort of a stricter Pearson correlation coefficient with the actual true voxel data. So we line up all of our predictions against all of the true data, and we draw a line of best fit, and you get penalized for falling off the line of best fit. And so what we're doing is Monte Carlo sampling of the posterior as well as the prior. And so think about, we're drawing samples of those diffusion and proliferation fields. We're solving our PDE forward in time, and we're computing these 2 quantities of interest. And so what you can see is that in the case where we look at the relative error in the tumor volume, the prior, which is sort of, think of that as like population level dynamics, performs much, much worse than any of the models that we calibrate to patient-specific data. So when we calibrate to the patient data, we're actually able to make, good predictions, right? So you can see 0 is firmly within these predictive envelopes. And so we're able to make, meaningful predictions about a patient's tumor burden 1 month into the future, whereas we can't do this if we just look at a population level approach. But from here, it's hard to tell, is daily more valuable than weekly? Is that more valuable than fortnightly? And so if you looked at sort of a stricter quantity of interest, the prior doesn't even show up here because it's so bad, but we can now see sort of a clear ordering between daily, weekly, and fortnightly. But what this might inform a clinician to say is, okay, well, if I need this level of accuracy, right, maybe I do need to use daily imaging or weekly imaging, or it's an argument for using more imaging. But it's not cheap, right? There's a significant cost to collecting this data. And so if you only care about something, sort of higher level like tumor volume, what is the total tumor burden, maybe you can get away with many fewer measurements, right? So you can try and think about, how should I order the measurement protocol so that I extract enough information to do well and make meaningful predictions, but keeping in mind sort of the cost and the patient time that's necessary to get those measurements. And so I'll just finish up with a couple things. I think that digital twins have potential to support clinical decision making in the future. I think this is a very nice sort of controlled setting. But I think that these sort of tools can be used sort of in the future, and it would be nice to really help enable improvement over these one-size-fits-all interventions. I think that personalized computational modeling requires tailored domains, and I think that we need to aim for a good level of realism here. And so that sort of starts with the computational domain itself. Bayesian approaches are really nice to rigorously quantify this uncertainty, because if you were to come to a clinician, you were to say, this is exactly what will happen, and then that doesn't happen, then I think you lose trust. But I think these sort of approaches where you quantify the uncertainty help to build trust and make it make it obvious when you have a lot of evidence to truly support a decision, and then when you might not. And then I think that this, sort of framework I presented is an efficient way to integrate medical imaging with our computational model. And then we have a flexible implementation that allows for alternative models. So the Fisher KPP equation that I showed you here today is not, there are many possible tumor models that you could propose. And I think that this sort of framework is very flexible for those different models. Future work is sort of one branch of it is, okay, we have uncertainty and we now want to sample from the posterior, but if you do that with Monte Carlo, right, it has sort of this 1/√n convergence rate, which could be quite slow. And so I've been looking into quasi Monte Carlo methods with some collaborators where you can get linear convergence. And so we have some initial results here where quasi Monte Carlo does quite well for this problem. I also think it would be interesting to look at more realistic models of tumor growth. So integrating novel data sources, things like MR elastography, incorporating mass effect. So as the tumor grows, it displaces healthy tissue, builds up a stress response, as well as the vascular development. And then there's a lot of work still to be done on, Gaussian priors are nice for sort of theoretical reasons, but there are other choices you can make for the prior, as well as optimally designing experiments. So I don't just sort of delineate between different imaging routines, but I am actually part of that feedback loop where I'm saying now would be a good time to image. And I'll just conclude by thanking sort of my sponsors, DOE CSGF, our great collaborators at the Center for Computational Oncology, as well as this M2DT grant. And with that, I'll take any questions.
That was a great talk, Graham. Thank you so much. I have a question about the priors. I think in slide 27. Do you think prior is not so important for this work, like for this study? Like no matter what the prior is, all the methods are kind of like converge to the same conclusion.
Yeah, so I think you need to have, so I think the prior is less important if you do this Laplace approximation, because you'll solve this deterministic inverse problem, and so you'll move sort of the center of that prior, right? But I do think it would be nice to have a much better prior, because then that inverse problem itself is easier, or if you were to go and do sampling, you'd just be much closer to the posterior. And I think that there is I think data-driven priors here would be really nice. So if you could sort of delineate your cohort and say, okay, you are a fast progressor, or your tumor is very aggressive, and so your parameters are likely closer to this range, as opposed to someone who responds well to therapy, who doesn't have a very aggressive disease, right? Those are sort of two profiles that I would imagine are quite different.
Yeah.
So I think there is still like a lot of use in developing better priors. But for this specific study, it's true that once you have patient data, sort of that is going to override the prior.
Yeah, that's really interesting. I also have a question about data collection. Because I'm not working in this area, and I was curious, how hard is it to collect all the data, or what is the rate, and like how long did it take you to collect all the data that you just showed in this presentation?
Yeah. So I would say I'm very fortunate to have very good collaborators. So I didn't have to collect any of this data myself, right? So we relied largely on public data sets. So there's a public data set, UPIN GBM, which it doesn't have longitudinal data, but it does have sort of many thousands of patients. They were treated, I believe, at the University of Pennsylvania. So it has sort of the images that I need to be able to make this work. There's also a historical data set that we used, this Ivy Gap data set from the late 90s, early 2000s. which does have longitudinal data, is very nice for this framework. So the data sources that I use are sort of those which are sort of put together for this express purpose. But I do know that we have collaborators that work directly with MD Anderson, and so they're getting patient data as it's sort of coming in. But it's like I mentioned, there really is a cost, right? So every time you want to go and collect this data, it is probably about 2 hours that a patient has to sit in a machine. And as you can imagine, there are lots of people that want to get in these machines and get imaged, and so then it's a major scheduling problem as well.
Yeah, that's really interesting. Thank you so much.
Hi, Graham. Thanks for your talk. It is very inspiring. I want to ask, in your Bayesian analysis, how do you define your likelihood functions for the uncertainty analysis?
Think that a simple thing there is.
Yeah, so because we use this additive Gaussian noise sort of assumption that the data is going to be the model plus noise, we can explicitly write down the likelihood function, and then it has this form where it's basically the model data misfit, where we weight by the noise. So you do have to know sort of what your noise level is, and you can try and estimate that through some kind of cross-validation study if you don't know. But if you say, if this wasn't a medical setting, but it was a setting where you had, maybe a strain gauge or something, that would be exactly the tolerance that the manufacturer tells you for the strain gauge.
Okay.
But
And also, do you need to define a kernel functions inside?
not here, no.
Okay, I got you. Thank you so much.
Yeah.
I can ask a couple more questions. Can you talk a little bit about collaborating with the Center for Computational Oncology?
Yeah.
Just like
So
some general information about your work.
yeah, absolutely. So they're great. I would, highly recommend everyone, if you have the opportunity to collaborate with them, collaborate with them. Everyone is great. Very, very, very nice. Very, very, very helpful. Very, very generous with their time. I think it's something that I've really come to appreciate about the Odin Institute, is that just how interdisciplinary it is and how easy it is to sort of collaborate with people from all kinds, different disciplines and domains. When I came to graduate school, I didn't think that I would be working on computational oncology, and I sort of had, I had the CSGF. I was very, I was sort of a free agent. It's like I could work on whatever I wanted to. I found this very inspiring and very interesting. And DCO, they were very nice and sort of let me attend meetings and, sort of really get involved to the level that I wanted. So I think they're great collaborators. They have a great network that they've really built up, where there are lots of projects that are actively, working with clinical trial data and trying to really not just think about things on the theoretical side, but actually really get involved on deploying these things in the clinic.
As a computational mechanics person and who is working in oncology, what do you think a big trend will be in the oncology in the upcoming years?
Yeah, that's a really good question. Um, I think model development will really improve. So I think this is what I presented today is sort of the simplest model you can derive, right? And I think that there's a lot of work that can be done as we learn more about this phenomenon, about how you should model these processes. So how do you account for the vasculature? How do you integrate new data sources? Because we're always coming up with new imaging sources, new ways to sort of probe and see what's going on. But I think two really exciting directions that are sort of not captured by this model right now are immunotherapies. And so I think that they're, especially with mRNA vaccines, there's sort of new classes of immunotherapies that are coming out, and it would be nice to be able to model those. And then it would also be nice to be able to incorporate genetic information, right? So how can we break down cohorts into subpopulations so that we can better tailor and tweak the models for individuals? So I think that those are really exciting directions.
Yeah, and I think you also mentioned in your talk, like uncertainty part is also really useful. So incorporating all of it will be really nice. Another question is for graduate students, actually, just very general. How do you tell when a PhD student is truly ready to graduate?
That's a good question, because yeah, like you said, I'm a final year PhD student, so I guess I'm approaching that time. I think that there's a lot of different answers to that, right? So some can be as simple as I have a job lined up and it's okay. Like, yes, now it's time to
That's a
graduate.
simple answer, yeah.
But I think it's hard to describe. I think you as a grad student will feel like when it's when you're ready to graduate, when you feel like you have a good handle of sort of the field that you're working in, and you're coming up with research ideas on your own, and you sort of have the confidence now to go and sort of implement your ideas and explore things on your own, right? Because I think the PhD is largely about learning how to learn, as well as becoming an independent researcher. And sort of when you can tell that you've taken a much larger role in how your day-to-day goes and how you actually drive your own research, then I think you're probably getting close to thinking about graduating.
No, that was a really good answer. Thank you. And lastly, do you have any advice for current or aspiring grad students in computational mechanics?
Yeah, I think it's really nice to see what other fields are doing, because I think it gives you a better appreciation for how you're doing things and how you might be able to take ideas from those fields and integrate them. And I've been very fortunate, very spoiled actually by the Odin Institute. Just by virtue of being interdisciplinary, I get to interact with, oceanographers. I get to interact with people that are working on oncology. I get to work with people that are, studying and modeling earthquakes. And so you see that, there's lots of different ways to solve similar problems to problems that you might be having. And I think just having that breadth of experience and seeing how other fields tackle things, can really spark ideas in your own work.
Yeah, I think your research also shows like how we can apply computational mechanics in different parts, the different problems. So it was really interesting. Thank you so much, Graham. If there are no other questions, I think we can end our seminar here. Thank you again for your great talk and for your time. And
Thanks
looking
so
forward
much for
to
having me.
seeing your future work.
Yeah, this is
Thanks,
great.
everyone.
Thank you.
Thank you.